Yeah, assume that we measure now step response again from a PT1. This is U sub O H of t, the step response, and the final value is now not reached, so the curve ends before we are reaching this saturation point, the final value. Let's assume this is time point t2 and this is voltage u2. And the idea is, if the curve is offset cleaned, we need one additional point. The question is, which is a good point with which we can get a good solution. The idea is very simple. If you take the point exactly at t1, which is half of t2, then the solution of both equations of my exponential function is solvable. So let's write down the two equations. U1 is u sub ok multiplied with 1 minus e to the power of minus t1 divided by t, and u2 is second equation, same factor, 1 minus e to the power of minus t2 over time constant. Two equations with two unknowns. K is unknown, t is unknown. T1, T2 is measured, U1, U2 is measured. So we have two nonlinear equations which can be solved in the following way, also without intermediate steps. The resulting point is u sub ok is, I look in my paper, is u1 divided by 2 minus u2 divided by u1. Yeah, so this ratio quantity, and the time constant then can be calculated by negative t2 divided by the natural logarithmic function ln 1 minus voltage u2, voltage point measured, divided by the result of the previous equation. So with these both equations you can calculate the K value, the DC gain, if you know the input voltage amplitude and the time constant of the system without knowing the final value. And this can shorten the measurement time dramatically, because here, you know, the measurement time here is 3 to 5 time constants. Here we can stop measurement much earlier. To show you the problems which can appear if you are too short, should be demonstrated by an example. Yeah, example. Model A. Note, now I want to test this experiment. I test with this simple testing method. I rent a model A, make a measurement, and identify the model and compare then the numbers. Example, very simple. I take a PT1, U1 input, U2 output, K is 2, time constant is 2. I do this example in two ways. First version, stop after 2 seconds. That means the time constant is 2. If I stop at 2 seconds, I'm at the 63% point after stopping the curve, so I need much more waiting time to get the final value. So this is rather early, and in the first version I give you the numbers and the results. Yeah. So first we need the resulting points. Of course, we can use a simulation program or the graphical curve. Say U1 is 1 volt. We want to have the unit step response. Then our step response works like k times 1 minus e to the power of minus t over unknown time constant. I just I take rec C# very quickly to get the points. Yeah, use rec C# to get the points very quickly. Now we can start this program easily. Yeah, I've started rec C#. Click on the US flag button to get English text. Put my PT1 here. Say block gain 2. Time constant is 2. Say OK. I add 1 branch and then start calculation of the step response curve. So we want to have time range of 2 seconds. I have just 1 block, 1 input, so just this is the step response. And here you can see really that the curve needs some time to get the final value, but you see that this is a little bit different to a straight line curve. So I need a point here at 2 and I need the point at 1 second. To get the calculated values, we can open the table and look for the time points. Yeah, if you click on this button, then you can toggle between the curve and the curve values. So I open the curve values and note the point at 1 second. Not exactly, so you see we have to decide a value between both curves. Say I take the first one, yeah, 0.78587, open 78587. So we have U1 is 0.78587 at T1 is 1 second, round about 1 second. And then I read in the same table the time at 2 seconds. Now I shift the table here into the field of the video. That is the last point, 1.26439. 1.26439. 1.26439. So these both points into these equations delivers values. I can use a calculator to put these values or I can use a tool. I have prepared a tool, C tool in WinDF C#. There is an identification menu, identification, and I opened it because in this chapter 8 we will go through many of these menu points in WinDF C#. So I open WinDF C# and show you where you can find it, and then we put these numbers into the program and calculate the identified T and K. See, I have opened WinDF C# and there is an identification menu. And if I open this, you see several points. Most of these points I cover with my lecture. So what I want to show here is the chapter 8.1 last method is realized behind these points, PT1 identification. Here the program asks for the 4 values, and then you can click say return button, and then you get the resulting values here in DC gain and time constant T1. So I type in the values and then we will see the result. So T1 is 1 second, U1 is 0.78587. Automatically this program doubles T1 time to T2, and this U is 1.26439, and with the return button I get the resulting numbers. Here you see the DC gain is 2.0094, and the time constant is 2.0157. So you see really rather good result, because the original values, if we can compare these with the original K and T values, the original K here is 2 and the original T is also 2, so the error is less than 0.5%. Yeah, so I write the result. Resulting K is 2.00941. Behind this module just are the equations we have developed here in this chapter, 2.01575. You see in this tool there is a sensitivity button. This is helpful to see what happens if I make an error in the measurements. You see, if I change this by plus or minus 1% and the U1 value with 1 or plus or minus 1%, then the resulting error in the calculation is larger than 1%, 3%, and here 5%. So there we have an error propagation. Simple 1% error here makes the 3 or here 5% error there. So of course a noise caused insecurity in the resulting numbers. That will be more severe if we stop earlier. So let's do the next second version of this example. If we stop earlier, then noise error will be larger. To demonstrate it, I just stop now the second version. Stop after 0.1 second. Yeah, so just 10 times earlier. Look for the resulting values. Now, calculation of points. I calculate now the curve, now up to 0.2 seconds. Make a recalculation, and what happens, you see in this resulting curve, the result is a curve which looks nearly like a straight line curve. And what we can say to analyze this identification method, if with your eyes you can't see any difference to a straight line curve, you should forget this method. Yeah, if this is a straight line curve, then know that the point here has a voltage which is double as large as this point, and if you put this into your equations, then of course, if you go back, if U2 divided by U1 is 2, you divide by 0, and of course then you can imagine the noise to signal ratio, the error propagation is very large. But let's do this. We have this curve. I click on the table values and calculate at 0.1 second. We read this value, 0.097358, and the value at 0.2. And I note these values in my paper. U1 is 0.09735, what was this? 6.8. At T1 is 0.1 second, and U2 is sorry, I stop after 0.2 seconds. That is wrong. I stop after 0.2 seconds. So this 1/10 of the time constant, because T2 is of course 0.2 seconds. 0.2 seconds. I read the value in my rec C# window. You see at 0.2 we have 0.190329. 0.19 warte mal, falsch, 0.190329. So if we put these numbers into my program, we will see what happens with my identification. Now we have T1 is 0.1, automatically this time is actualized, but here we have now U1 is 0.9735, and here we have 0.190329. If I click on return, you see now, okay, K is 2.16, and here time constant is 2.17. Seems not too bad. I write the result. K is and T is, the identification throws out 2.16816. T1 is 2.1768. But note, if I click on my sensitivity button, you see that I have an error propagation of factor of 30. 1% change here gives 30% here. That is, of course, a large error propagation. But you see, my eye sees a straight line curve, but the values, I think the last digits here are important for the calculation, gives not unacceptable result. Error propagation is large, but large error propagation. %1 leads to a 30% error in results. 1% measurement error changes my resulting values with 30%. Okay, so far.